Hi, hello there, and welcome back to Steaming with Steve. Today we're going to go through terminating and recurring decimals. Now, these are numbers that either have patterns that repeat on forever or have finite finished points. So terminating values will always finish at a value, whereas recurring decimals will have a sequence or pattern that occurs within it. So let's dive on in. So to start, just a little bit of a warm-up from some of the activities we've done so far. So just pause the video and have a go at these guys. So for the first one, you should see that they have exactly the same denominator. So therefore, you just add the numerator. So now we're going to do 5 plus 3, which gives you 8 on 10, which then reduces down to 4/5. And then this one here, hopefully you can see you got 6 on 9. You would reduce that to start. So you got 2 on 3. Then you just do 2 times 2, which gives you 4. And then 3 times 1, which gives you 3. This one here, again, you can reduce this. So you can divide both the 8 and the 40 by 4. So you should do that. So that reduces down to 2 on 5. And then when we divide, we flip this side. So that becomes a times, and then we times this by 4 on 3. So we have 2 times 4, and then 5 times 3, which gives us 8 on 15. This one here, we're going to add line it up with the decimal point. So 2 and the 4 needs to be underneath each other. And when we add those together, you get 6.49. Second last one, we're timesing this by 100. So we know we're timesing by groups of 100. We just shift the decimal point. So we count how many zeros. So there's 2. So we're going to go 1, 2. So it's 398.7. This one, when we divide by 100, we count the number zeros. So 1, 2. So this one time it's going to go the other way. So it's going to go 1, 2 back and give us 0.0445. Awesome. So when we're dealing with decimals, they're really important to understand because they help us understand currency and measurements. Those are the two big ones that happen that you'll see a lot. So we need to understand the difference between a terminating and a non-terminating, particularly when we're timesing and dividing, because they can pop up from time to time. So to understand the difference between terminating and non-terminating, terminating decimal is really easy. They have an end after a certain number of digits. So if we did 1 divided by 8, it just equals 0.125. There's nothing else after that. Whereas if we have a non-terminating or repeating decimal, these are patterns that keep on going forever and ever. So for example, if we do 1 divided by 6, it equals 0.1666666666666, and that would keep on going on and on and on. So that's the main difference. So when we divide, sometimes we'll get fixed values like this, and other times we won't get such a nice clean sort of cut. So with decimal expansion, you've got different types. So you've got terminating, non-terminating, and then inside non-terminating, you've got 2 different types. So you've got repeating patterns, which is what we just looked at, and then also another thing called non-repeating patterns. Now, the best example of that you've seen so far is probably pi. So if you talk at the circumference of a circle and you know the diameter, you would times the diameter by 3.1415, and you should be able to get that circumference. Cool. So when we're dealing with non-terminating decimals, we have 2 different options. So we have the dot or the hat. So if you have a dot above the number, it just means you repeat just that single number. So for example, the 4 would repeat on forever. Whereas if we have the hat, it means we have this nice bar over the whole thing, and then that pattern or sequence gets repeated over and over. So 1579, 1579, 1579. That would keep going on and on. So just pause the video and have a go at these guys and see how you go. Cool. So first one, 7 divided by 8, you should go to non-terminating. So you should have got 0.825. 1 divided by 4, you should have got 0.25. Then for the rational number, 1 divided by 3 would give you 0.33333 repeating. And then pi, hopefully you've used your calculator and you got 3.14159. Cool. So a little bit of an exploration now. Just pause the video and have a go at that and see how you go. So 5 divided by 8 it gives you 0.625, which then hopefully you notice is a terminating decimal. Pause the video, have a go at that one. So this is a repeating pattern one again. So 3.142857, and then the 142857, 142857. That repeats on and on and on forever. So that is a non-terminating decimal. And then it's also something interesting, just a bit of history. That is what some people used to use for pi, because it does give you a quick approximation for it. So then if we want to calculate 13 divided by 12, you got 1.08333333. This is again a non-terminating decimal. Cool. So there's a bit of a Python program I put together. It's kind of cool. What it does is it allows you to work out decimal numbers and see the pattern past what you can see in your calculator. So in your calculator, it will only ever go up to probably 8 decimal places, whereas this little program can go up to 100 decimal places, which is really, really, really cool. So you don't have to understand it necessarily, but if you want to play around with it, you can copy and paste this code. And yeah, let's have a go. So with this little demonstration, if you did 1 divided by 7, hopefully now you can see the nice cool little pattern that goes on and on and on. And that pattern will go on forever. It doesn't finish. So the 142857 gets repeated. 142587, 142587, and so on, all the way to the end of time pretty much. So that's useful. So if we had, I don't know, to measure, the distance from here to the nearest star, the number of decimal places that you put behind that is kind of useful because you can see a little bit more accuracy in how far they are. So a little bit of a challenge. Just pause the video, have a go at these guys. So if you did 1 divided by 4, you got 0.25. 1 divided by 5 gave you 0.2. 7 divided by 8 gave you 0.875. 3 divided by 16 gave you 0.1875. And then 5 divided by 2 gave you 2.5. The next ones, so these were all not terminating decimals, whereas the non-terminating ones here, 1 divided by 3 gave you 0.3333 repeating, or just 0.3 with a dot on the top. 2 divided by 9 gave you 0.2 repeating. 7 divided by 6 gave you 1.16 repeating. 13 divided by 11 gave you 1.18 recurring. And then 22 divided by 7 gave you 3.14, 2857, 142857, 142857. And that pattern would repeat on and on and on. Kind of cool. If you saw the 1/7 as well, you can see there's a nice little pattern there. So then these ones are a little bit more interesting. So it's 13, hopefully you saw when you did 2 divided by 9, that the 2 just repeated on. And then if you did 3 divided by 9, which is the same as the third, see how it does the 3 repeating. So when we do 13 divided by 99, what happens is it's just the 13, 13, 13, 13, because it's got 2 nines on the bottom. So two numbers on the top and 2 numbers on the bottom with 9s. We'll do that repeating. Similar with the 24, exactly the same pattern. So 24, 24, 24, 24. And then 837, because it's got the 3 nines on the bottom. Again, that top will just repeat itself. Same with the 382. And then even this one here, as long as it's got as many numbers, 9s on the bottom as it does on the top, that pattern then repeats. So 0.3893, 38093, sorry, would repeat on and on forever. So these are really important calculations, particularly if you're interested in the building industry or any architecture sort of thing, because if you're off by, usually you'll measure down to the millimeter. So, and if you're off by that, there can be some huge structural issues that go on site. So it's really, really important that we have those measurements and that we're rounding appropriately and understanding those little patterns that happen underneath. So just pause the video and have a go at these ones. So for the first one, 3 divided by 5, that gives you 0.36. 3 divided by 4 gives you 0.75. 1 divided by 8 gives you 0.125. 11 divided by 20 gives you 0.55. 1 divided by 3 gives you 0.3 recurring. 5 divided by 9 gives you 0.5 recurring. 5 divided by 6 gives you 0.83 recurring. 8 divided by 11 gives you 0.7272 repeating. And then when we round these guys, we get 17.01. 0.92 because we round up because of the 9 next to the 1. 0.444 becomes 4.44. 14.51 then becomes 14.52. 5.19 becomes 5.20. 78.99 rounds up to 79. But notice that I've still put the zeros in because it's saying to 2 decimal places. 0.0015 becomes just 0.00. So that's the most accurate value that it is closest to. And then 2.68 leaves 2.68. The last thing I want to show you is a little bit of a problem-solving question. So just pause the video and see how you go with this. There's a little bit more challenging, probably a year 10 sort of level, maybe even year 11, and see what you can do. So prove that 1 is equal to 0.9 recurring. Cool. So usually I give about a minute or two just for people to struggle with this first. The hint here is you use algebra to fill in the blanks. So I'm going to go x is equal to 0.9 recurring. So x is equal to 0.9999999. And remember that goes on for all the way to infinity. So if we times both the sides by 100, you would now get this little interesting fact. You would get 100x, because this is times by 100. And if we times this by 100, we times the other side by 100. That just means we shift the decimal place to the right. So that gives us 99.9 recurring. Then, because we've got 0.9 is equal to x, we're going to take an x away from both sides. So I'm going to subtract 0.9 recurring from both sides, which then gives us 99x is equal to 99. So because x is equal to 0.9 recurring, we've taken that away. And then if we divide both sides by 99, we then get x is equal to 1. And then you can jam a QED at the end. So that proves that the by writing QED is a really interesting fact. Basically, math nerds will write this at the end of any demonstration. It's Latin for quod erat demonstratum, which roughly translates to that which is to be demonstrated. Now, math nerds love putting this after a proof because that shows that we were right. So just running QED is a kind of cool thing that you can add at the end. Cool. So that's pretty much it. There is a Dr. Frost available for non-terminating decimals. Highly recommend having a play with that and getting your head around that. So if you did enjoy this video and you understand now the difference between terminating and non-terminating decimals, I'd really love for you to give us a like and subscribe down below, and also hit the notification button so you can see when any of the new content pops out. That's it for me. Thanks again for watching, and see you next time on Steam It with Steve. Adios.